Well, good morning, good afternoon, or good evening. Wherever in the world you're joining us from today, welcome. This is the fifth in our series of OpTek webinars, and today's session is titled Precision Laser Micro Milling of Hard Materials. A quick housekeeping note before we get started. Today's session is being recorded. We do welcome questions at any time. Just use the question box in the top right of your screen, and we'll work through as many as we can at the end. For those who haven't joined us before, I'm Alan Coleman, your host today, and QHSE and UK Site Director here at OpTek. My background spans the semiconductor industry, both in the UK and internationally, covering equipment engineering, sales, and commercial development. As always, let me give you a quick overview of OpTek for anyone joining us for the first time. We are a global provider of precision laser processing solutions, headquartered in Abingdon, Oxfordshire, with international operations in Greenville, South Carolina, Boston, and Dongguan, China. Abingdon is where our machine builds, micromachining, and R&D activity is centered, and Greenville is our home to our fiber center of excellence. Out of Abingdon, we develop and deliver custom laser processors and systems capable of machining a remarkable breadth of materials: ceramics, polymers, delicate organics, and much more. If a material can be machined, there's a good chance we have done it. Our origins are in optical fiber processing, end-face machining, cladding removal, and precision tasks that improve yield and optical performance. But our capabilities now span way beyond that. We support customers across the full life cycle of laser processing, from early R&D and prototyping right through to fully automated production systems. Working routinely at sub 300 micron feature sizes, our systems range from compact desktop units to multi-ton, multi-laser 5-axis platforms. The largest we've built weighs several tons and achieves sub-micron precision. Our Greenville site serves as the fiber center of excellence, focused on advanced fiber optic processing and assembly, stripping, cleaving, lensing, splicing, and the fabrication of and alignment of fiber arrays. We work across telecom, medical, defense, and sensing markets and provide system integration, training, and technical support for our North American customers. As part of the Humanetics Group, we have the financial strength to take on ambitious long-term projects. We hold 9001, 14001 certifications across our sites, and ISO 13485 for medical applications in our UK and China facilities, reflecting our ongoing commitment to quality and sustainability. Today, we're diving into precision laser micro milling of hard materials, and I'm really pleased to hand over to Andrew Lee, one of our applications engineers based in Greenville, who will be talking you through today's content, and I'll be back for question and answer at the end. So, over to you, Andrew.
Thank you, Alan. So a little bit about myself before we really get into the meat of today's discussion. As Alan introduced me, my name is Andrew. I'm an applications engineer at OpTek Systems here in Greenville, South Carolina. I got my start here specifically at OpTek in 2022. However, I've been pretty deep-rooted into the laser machining industry for a while now, making my start originally with Clemson University's laser laboratories. I've been working here with OpTek Systems, gaining my knowledge and applying my background and experiences in order to serve the biomedical, communications, aerospace, and defense industries, as well as many other industrial sectors throughout the world. The main thing that we want to start today is really to first introduce our challenge. The main thing that we're looking at is contact-based mechanical milling, especially at the micron scale. This obviously, with anything, but specifically on this topic, introduces a lot of challenges. A lot of the drilling and milling bits at the micron scale tend to wear out very fast and are very susceptible to deformation and wear, and they often break even with regular trained use. They also may induce damage to either surface treatments or material work surfaces. They generate high amounts of chatter and debris, which has to be managed either through airbrushing, vacuums, or any other management solutions. And in some cases, even with the assistance of CNC tooling, we often don't see that we get the most desirable or most in-spec tolerances and dimensions that we're looking for at micron scales. An example of this is what we see here in our bottom left, which is a partnership research project that we'll definitely be talking about later on in this presentation, where we can machine hardened titanium and hardened materials, but often our edge quality and our wall quality may not be getting us what we want, or they may be heat or fracture effects that are negatively affecting what will be the final workpiece. Which pretty much moves us straight into our primary topic for the day, laser machining of hardened, be it inherent or surface treated materials. So micromachining with lasers specifically has many advantages to it, especially as it relates to high Shore hardness rated materials. It's entirely light energy based, which in turn means that it's entirely contact free. Um, the use of galvanometric mirror systems means that we have high speed, high volume output of our working materials and conditions, as well as being able to very precisely and consistently produce micron scale features and tolerances, even with these most resilient materials. The fact that we're using an ablation-based process also means that our debris is highly controllable and manageable, as well as the fact that we have a high awareness of how heat is generated and affects our materials. An example of what we can see in this in application can be shown in the top right pictures, where we're looking at a case hardened steel sample, which has been milled to very specific dimensions with minimal heat effects to the actual edges of the workpiece, and no deformation or residual, excuse me, debris effects. For our first example of a real-world application of laser micromachining for hardened materials, we're looking right here at a gas pneumatic bearing or hydrodynamic bearing. These systems are usually made up, in this case, of shafts of molybdenum, but they're also made up of titanium and case-hardened steel. Often, these systems require very specific machining and with very high low tolerance requirements for the patterns and groovings. What this means is that they have to be repeatedly produced, and we have to make sure that we're doing it as consistently and verifiably as possible. What we see right here is that OpTek's laser applications labs are able to integrate coordinated motion systems. In the case of what we see here, both linear drive systems and rotary systems in combination with our galvanometric scanners. What this gets us is a high amount of controllability with what we're marking, as well as the ability, as we can see in our bottom right-hand corner, the ability to use inspection tools to verify and certify the quality of our work. Another example of of this same topic right here is that with a lot of these pneumatic bearing systems, a lot of them have very specifically treated surfaces with high amounts of polish or with surface treatments. What this means is that we have to minimize the amount of post-processing done in order to preserve those treatments and qualities. OpTek's laser applications labs are able to preserve this by the simple fact that with laser micromachining, we are able to produce features that are nearly ready to go to work right off the laser. This means that there's less post-processing and less post-processing treatment that has to be performed, which could compromise the engraved features on these workpieces. Another application that we're going to talk about for these types of materials is medical applications. A lot of medical applications requires that components be designed and produced with low amounts of burr and debris, as a lot of these materials may be compatible with biological environments on a large scale and on the tool scale, but fragments and debris are less than desirable in these environments. As such, as previously mentioned before, ablation-based machining gets us that quality where we're able to have hyper amounts of control over our debris, and it is highly manageable for us. Another example of one of the really strong advantages of laser ablation, especially in how OpTek systems is able to really make the different systems work together in collaboration, is with what we see right here with helical probe tubes. These probe tubes have a outer diameter of about 90 microns and an inner diameter of about 80 microns. So these are very susceptible components to deformation, even minor deformation from contact-based solutions, which in this sense makes a contact-based milling solution impractical or quite simply not possible. With laser-based machining, we're able to get these micron scale precision while doing coordinated high-speed motion with high repeatability and with verifiable quality. Something that isn't really to say that OpTek is unable to do work in with classic contact-based machining. Quite the contrary, actually. Our research laboratories, as well as our system integrators, are able to do what we call laser-assisted machining. What this essentially is our ability to integrate our experience with laser systems with our knowledge and experience with traditional contact-based milling. What we see right here is a partnership that we did with the University of Nottingham and Edinburgh Medical, where we're processing titanium silicon matrix materials, which alone with laser machining would work, but it would be very time intensive to do this processing. But at the same time, if we were to use only exclusively contact-based milling, we may not be getting the quality that we're looking for. In collaboration of these two ideas, we're able to actually get a process that both gets us the quality that we're looking for, as well as the performance, the time performance that is desirable in a large-scale manufacturing environment. As I mentioned before, we have systems and capabilities not only to perform all of these laser-assisted machining capabilities, but our laboratories also have the ability to verify our quality and to consistently prove it. As we can see right here, we're able to monitor our quality down to the metallic grain, in which we can even compare. This is what it looks like, as we can see in our pictures to the right, when we machine a workpiece with only contact-based solutions versus when we use the laser-assisted milling solutions, and we're able to achieve the uniformity that we're targeting, as well as the dimensional quality and the dimensional tolerance that has been set up in our designs. Now, something to really understand is that a lot of these materials are high shore hardness and are very difficult to work with. A lot of our previous examples have shown that are sometimes on the micron scale, even when we're doing high volume. That isn't to say that OpTek isn't capable of doing high volume procedures on high scan areas as well. As we can see right here, we have a webbing matrix that we're machining with our laser systems that are able to produce results and quantities up to 30 meters per minute. So these are systems that are both our research laboratories and our system integrator teams are really able to generate processes and systems that are highly tuned to our customers' needs. So really just to kind of cover a summary of what we've covered, because in a practically short amount of time, I've covered a lot of content. The main things I really want to hammer home is that a lot of systems, especially in the modern day, require high shore hardness materials, either through inherent alloys or with surface treatments. There are a lot of challenges machining and working these materials because of this. As a result, sometimes it's not always practical to use traditional milling solutions. With today's galvo-driven ultra-fast pulse laser systems, we're able to do both process development, system integration and volume production, whether it be in-house in our laboratories in Greenville, Abington, or Chelmsford, Massachusetts, or to actually build tailored systems for our customers to have in their own workplaces. A lot of these technologies that I've shown today are really driving us forward, both in terms of laser technology as well as the future of manufacturing in general. This is something that OpTek continues to support, both with our research partners and our customers, to really ensure that we're at the forefront of this capability, whether it's from the oil industry, the aerospace industry, or the medical industry. OpTek is pretty much there at every step to ensure that anything is possible with the right mindset. So, like I've said, we've covered a lot of materials, but I think what we're going to do right now is take a pause on things and do a QA with Alan to see if there's any questions that have come up during our presentation.
Thank you, Andrew. A really strong presentation and a great demonstration of the technical depth we have here at OpTek. Okay, so we've had a few questions come in. Let's move forward to those. So the first one that's come in, Andrew, is what kind of surface finish can you consistently achieve, and does it require any post-processing?
That's an excellent question. So we get a lot of different surface finishes that come into our lab, and as well as customers who ask us to work materials into specific surface finishes. Something to really start with is that with our example that I showed earlier with those polished molybdenum rods, those come to us with a RQ roughness of about 100 nanometers polish. This is something where a laser milled finish can consistently work these to about 200 nanometers in RQ roughness, which is a really strong advantage in comparison to a lot of CNC contact-based solutions, which on average seem to only get finishes of around 600 to 900 nanometer in roughness. What this allows us to do is, if that's what our customer is asking for, is that we can create surface finishes that are ready for work right off of the laser bench.
Brilliant. Thank you, Andrew. Another next question is, how thin can you make a micro hole array? Now, this question, they've said, I want to make a 30 micron hole with a thickness of less than 10 microns.
So that's one of our specialties right there. Is a lot. We have a lot of experience with micro hole arrays, especially very close to those dimensions and tolerances. To kind of answer the question on a bigger scope, typically the thicknesses that we really start to see challenges with are in excess of about 3 millimeters in thickness. That tends to be where we're starting to reach the point where, okay, we need to take another look at this and really get an idea of what these high ratio marking is getting us. But in terms of the answering the question itself, yes, we are able to do 10 those micro hose at about 30 microns in diameter.
Okay, next question in. How does laser micromachining compare to CNC machining when it comes to achieving tight tolerances on harder materials?
Okay, so that's actually another excellent question. So with a lot of CNC systems, especially in the modern day, we typically see tolerances on the mechanical side that range on the area of plus or minus 200 microns in dimensional tolerance. And typically, if we want to go further on that, we can see a precision and reaming tolerance of about plus or minus 50 microns. One of the advantages actually of laser micromachining is that that's essentially where our tolerances start. We set our basic standard at plus or minus 50 microns, and we have worked with a lot of customers over the years who have asked for tolerances all the way down to the single digit tolerances, such as plus or minus 2 microns.
Okay, fantastic. Next question. Are objective lenses built into your laser processing machines? If so, what types?
That's an excellent question. So the objective lenses that we work with are designed to work in collaboration with our galvanometers. And so that gives us the ability to interchange our lenses as we see fit, whether it means changing our wavelengths or trying to get a larger scan size or get smaller spot sizes. So we're able to build these lenses into our systems to really accommodate anything that we need, whether it's telecentric lenses or any other type of lenses. Like I say, our research laboratories are purpose built to be as flexible as possible.
Brilliant, thank you. Coming in thick and fast, here's the next question. Are there limitations on material thickness or depth when using laser micromilling?
So those limitations, as we kind of mentioned a couple times before in the presentation, there are some limitations. 3 millimeters in thickness tends to be where we start to see challenges, especially on these harder shore hardness materials, especially with these metals. That's typically where we start to get into the expertise of our labs on high ratio marking, where we're able to get very small features, but very deep into working materials.
Brilliant, fantastic. Another question, can you machine glass?
So yes, machining glass is typically one of the more difficult crystalline structures that have to be worked on across the entire laser industry. However, our teams in the laser micromachining departments here at OpTek Systems have become very well acquainted with working this material, whether it's traditional glass or tempered glass, or even special crystalline structures such as sapphires or rubies.
Brilliant, thank you. Next question, is the laser assisted machining example with MMC in the laser assisted machining example with MMCs, how transferable is that approach to other composite materials like CMCs?
So that's an excellent question as well. To put it very simply, it's very transferable. Many composites CNCs that we see out in the industrial world tend to have very similar working properties to these hardened metals and surface treated materials. A lot of that also basically means that it's very difficult to work those composites with traditional contact-based milling methods. But in the OpTek's applications laboratories, those are things that we work with every single day.
Brilliant. What is the smallest feature limit? Simple question there.
Okay, the smallest feature limit, that tends to be reaching, honestly, it depends on what the feature is. If we're doing micro holes, we can do them down to the single digit microns in diameter. If we're doing specific patterns, now we're starting to reach the area where it really depends on the wavelength we're using and what the desired dimensions are. Um, Typically, in my experience, we've seen the smallest features being squares and circles and dedicated patterns of about total diameter of maybe about 5 microns overall. A
Okay.
lot of that really is based on the spot diameter that the customer is asking us to use.
Okay. Fantastic. I think that's one more.
Okay.
Can this process be scaled for high volume production, or is it more suited to prototyping and low volume runs?
So that's an excellent question as well. Um, as we might have seen over the years and kind of inferred in this presentation, sometimes we see a lot of small scale or small volume systems that are trying to really figure out and do research on a concept. That really isn't to say that we can't do volume. In fact, in many cases, our customers and partners come to us with the idea that they want to figure out what the process is in order to make their design work. And then once we're able to develop a process and routine for it, they're ready to say, okay, that sounds great. Let's go ahead and build a volume system or a speed system in order to do this in high quantities and high volumes. So really, a lot of this is scalable, and OpTek is really there to kind of take our partners from concept to production at any step and any service we need to.
Brilliant. Thank you, Andrew. I'm just scanning through. I think that's all of the questions. So that brings us to the end of today's session, the fifth in our OpTek webinar series. A big thank you to Andrew for a brilliant presentation, and all of you for joining us and your interesting questions. The recording will be available shortly, and we look forward to seeing you at our next webinar. Thank you.
Thank you very much, everybody.